Yes, I guess we have to slideshow. Just turn on the laser pointer. Yeah. Hello guys. Good evening. Thanks for joining for this live problem solving session number 2 for the course Analog IC Design, which is being conducted by Professor Sankaran Aniruddhan from IIT Madras. Just to introduce myself again, I am Soham Lakhote, currently a fifth year PhD student at IISc Bangalore, working under Professor Gaurav Banerjee in the areas of FMCW radars for vital signs monitoring. Right, so again the session organization will be exactly same. We will first take the session for first 50 or 60 minutes. We will have a short break of 5 or 6 minutes in between, and then again we will resume back our session. Right now, just for the standard disclaimer, this is the YouTube channel where I will be uploading all the lectures, and in the description section of each and every YouTube video you will be able to find the link for the presentation folder where all the lecture slides will be uploaded. So if some of you are not able to access this, or you have joined the session for the first time, then during the break please let me know to post this link, to copy paste this link into the chat section of this Google Meet. Right now, the organization of this today's session will be first, we will be solving few numericals on the negative feedback. During the last lecture, I gave you a complete overview of what actually goes into the transceiver design, where does the role of the analog engineer comes into the picture, why analog and RF jobs are not gonna go anywhere even if the automation comes into the picture and all. Right, so now it's time to get our hands dirty and to solve some problems, right? Because you guys have to solve some assignments, and I guess their deadlines will be few days away. So now what we'll do, we will just take few problems on the negative feedback. Sir have taught you about the loop gain analysis, right? So we will try to take a case study of a low dropout regulator and try to see how that loop gain analysis comes very handy in trying to calculate the power supply rejection ratio. Don't worry, we won't go into too much depth. I will try to make it in such a simple manner that even if you have just taken a basic course on the analog circuits, you will be able to understand this case study. Then we will take some problems on the passive RC filters as well as the active RC filters, because I saw that in the second assignment you have been asked questions on that, right? So I don't want you to feel that sir has not covered that part and they have directly asked the questions. So we will try to get familiarized ourselves with the passive as well as the active RC filters, and then we will, after studying all this, now we will try to go into some of the research papers and try to see where this passive as well as the active RC filters have been used, especially for radars as well as the communication transceivers. Right, I hope that everything, the organization is clear. So now let's try to have a quick recap of what has been taught in the negative feedback. Right, so now what is the difference between these two topologies? So if you look at this amplifier, right, this is a common source amplifier, and I assume that every one of you know what this common source amplifier is, right? So its gain is nothing but minus Gm into Rd, where Gm is the transconductance of this device M1. Right, now you know that when you try to fabricate a chip, right, there is something called as PVT variations. Now what are those PVT variations? So you know there is this is basically a manufacturing process, and every manufacturing process has some tolerances inbuilt into it. So you just cannot get the ideal structure that you want to actually fabricate, right? So what you will see, because of that, let's say you wanted, just give me a minute. Yeah, so you wanted a resistor value of maybe 1 kilo, correct? But you will see that after fabricating there is almost a plus minus 20% tolerance in this value. Now you go to the GM, right, and you observe that your threshold voltage itself has a variation around 100 millivolt. Now these variations will change the value of GM as well as the RD. So now what you will see, if I try to fabricate a maybe let's say 1000 samples, 1000 such circuits on 1000 different chips, right? So if you fabricate a common source amplifier, 1000 common source amplifier on 1000 different silicon samples, what you will see is that the gain that you are seeing over here, GMRD, so there will be some kind of Gaussian distribution around this GMRD, right? And what is this? So basically this is what is we call as a confidence interval, right? So now what you will see is that GMRD, the gain itself has some maybe 10 to 15% variation around this value GMRD, correct? Now what did we say? So let's try to do one thing. Let's try to put this amplifier as a A1 over here, and let's try to put it in a negative feedback, right? And what did this negative feedback actually do? So after putting this amplifier in the negative feedback, we got the output upon input equation to represent something like this, where beta is nothing but my feedback factor, correct? And that is independent of amplifier. So now what did we say? If my amplifier over here had sufficiently high gain, that means the product of A into beta, if it is much greater than 1, right? Very high value, not 1, very high value, maybe something like 10 to the power 5 or 10 to the power 6. Correct? So if I have this, then I can just ignore this term over here and my gain will be nothing but 1 by beta. So now I have made the gain of my system to be independent of any PVT variations that are gonna happen in this particular amplifier. Right? So now that is why we are using this negative feedback over here. So I hope this part is particularly clear. Now another benefit of this negative feedback is the bandwidth extension. So now, okay, I have this amplifier A1, right? It has a pole at omega naught, correct? So now if I try to plot a Bode plot of this particular transfer function, it will look something like this, right? Till this omega naught, my gain is A naught, and after omega naught, the gain will roll off with the slope of minus 20 dB per decade. Right? Now what happens if I put this amplifier in a negative feedback and having a feedback factor of beta over here, right? So now all of you know this, like what is the expression? A upon 1 plus A beta, and A over here itself is A of S, correct? So now when you put this equation in this particular equation, right, you will get some equation which looks something like this, correct? So what you can see over here, if I put S equal to 0, that means my DC gain, that means putting S equal to 0 in this equation will give me value of DC gain. If I put S equal to 0, this term will be left as a 0 and I will be getting this particular term, right? So this is in complete alignment with what sir has taught. The open loop, the closed loop gain will be reduced by the factor of 1 plus loop gain, right? And now at the same time, if you look what has happened to the pole has actually increased by the factor of 1 plus beta A naught. This is what you are seeing over here, correct? So even though your gain has decreased, but at the same time your bandwidth has increased over here. So if you just take the product of this gain and this bandwidth, so I'm gonna write one equation over here, a product of gain of the closed loop system into the bandwidth of closed loop system is equal to the product of the gain of the open loop system and the 3 dB bandwidth of open loop system, correct? So you can see if you multiply these two, the 1 plus beta A naught from the denominator over here and the 1 plus beta A naught from here are gonna get cancelled and you will be left with just A naught into omega naught. Similarly, if I do it for the open loop, the gain, DC gain was A naught, right? And the bandwidth was omega naught. So again, A naught into omega naught became true over here. So that means this equation holds true, and just give me a minute. Yeah. And this is only valid. Yeah, you have a doubt?
So can you sir please repeat? Yes sir. No sir. I want to say that sir. Can you sir please record this session?
Oh yeah, the session is being recorded. Just give me a second. Just a minute. See, you are seeing over here, I am recording the session. Yeah, just give me a second. Yeah. So now what you can see over here, this equation actually holds true, and this is only for the first order systems, right? Do not try to apply when amplifier has more than one pole. So if this is a 2 or 3 pole system, then this may not hold true actually, correct? So I hope this is clear. Now what is the application, what is the use of it, right? So now let's try to see, if I try to give a 20 megahertz square wave to an amplifier which has the gain of around 100, right? This is in absolute units, not in dB, and it has a 3 dB bandwidth of around 10 megahertz. Now if I try to give a square wave, what should I expect at the output? See, this is an amplifier. It will take certain time to respond to the input. What I am doing over here is I am instantaneously at time t equal to 0 changing my value of the input waveform from 0 to Vin, correct? The amplifier's output cannot do that. It will take certain time, right, to react to this particular waveform, right? And this is what you are seeing over here by this rise as well as the fall time, correct? Now we will do one experiment now. So now this gain of 100 and the bandwidth is 10 megahertz, right? Now I did something with this amplifier I put it in the feedback and reduced its gain by factor of 10. Now you know from the previous principle that if I put that amplifier in the feedback and if its gain has been reduced by the factor of 10, that means the 1 plus beta I naught value is equal to 10. So at the same time my 3 dB bandwidth has to go up by the factor of 10, right? So this is what I got over here. The gain bandwidth product, this gain bandwidth product and this gain bandwidth product should remain constant. So if gain has dropped by the factor of 10, the 3 dB bandwidth has to improve by the factor of 10. And now since I want to get a gain of 100 but my gain is only 10 over here, so what I will do, I will just cascade two of them. Right, I will just cascade two of them. Now let's see what has actually happened. Since this is a square wave of 20 megahertz frequency, right, and now my amplifier, if you look, this has a 3 dB bandwidth of 100 megahertz, this has a 3 dB bandwidth of 100 megahertz. So now if you try to calculate the 3 dB bandwidth of the cascade of these two amplifiers, there is a particular formula, but I don't want to go over there. Just see that the bandwidth has actually increased, the 3 dB bandwidth that I'm talking about. Now what we expect, if the 3 dB bandwidth of the amplifier is improved, then the way it reacts to the input, right? Let's say I gave the unit step, then you know if I gave a unit step function like this, right, then the output is gonna charge exponentially towards the final value. So now if I increase the bandwidth of my amplifier, this tau that you are seeing over here, correct, this tau is going to reduce now, and this is what you are seeing over here. The rise time and the fall time has considerably reduced. So this is the application of what you can say, this bandwidth extension that you can have in your head. So now before going to solve the problems, I just want to clarify a very few differences. It's a very basic one, but what are the properties of the ideal amplifier, the ideal op-amp? It has an infinite input impedance, a zero output impedance. Why zero output impedance? Because it has to act as a good voltage source. And what is a good voltage source? A good voltage source is a one where the value of RS is close to 0. Right, and at the same time, why do I want input impedance to be infinity? Because if I have a voltage source with me, some other voltage source, right, and let's say this is your op-amp's input impedance. Now if I want all of this voltage to drop across this RL value, the RL value should be as high as possible, right? So that is why infinite input impedance is the ideal property of the op-amp. Now we ideally want infinite gain, infinite bandwidth, but we don't get that in the practical world, as well as the offset currents offset voltage should be 0 between the two terminals of the input, right? So I hope that part is very clear. Now let's go into try and solve few numericals based on the op-amp. Correct. So now let's try to take this example. I have taken this example from Razavi's book. So now let's see what has been given over here. So now we have an amplifier which has a pole at omega naught, correct, and that amplifier has been put in the negative feedback configuration. And from you must have studied this, right? What is this amplifier? This is a non-inverting amplifier, right? So what will be the gain in the ideal case? 1 plus R1 by R2, correct? So that should be the gain of the amplifier in the ideal case. But will we get that? We won't get that because this A of S is not infinity over here, right? So now what we want to do, let's check the question what they have given. A small step has been given at the input. So now calculate the time required for the output voltage to reach within 1% of its final value. What unity gain bandwidth must the op-amp provide if the gain 1 plus R1 by R2 is close to 10 and the settling time is to be less than 5 nanoseconds? Correct? So from the week 1's lecture, you at least know that if the unity gain bandwidth of the amplifier goes higher and higher, right, it will take it very less time to settle to the final value. Correct. So now we have to, now what they have asked is they have given us the specification for the settling time, and now they are asking us to calculate the unity gain bandwidth of this particular op-amp, so that when it is being used in this particular configuration, it will satisfy this particular specification. And based on this final answer that you will be getting for the unity gain bandwidth, the op-amp designer has to design the two-stage op-amp accordingly. Correct. So this is just one very simple example that actually tells you what dictates the specifications on this two-stage op-amp. You must be seeing, you must be confused, like from where do we get the specifications of the op-amp, the 3 dB bandwidth, the gain, who dictates those values, right? So those are dependent on the application, and this is a very simple example for it, right? So now we have already studied the closed loop gain. We have already studied, right? It is nothing but A open loop upon 1 plus A open loop into beta. Correct. So now what we will be doing is we will take the advantage of this particular equation. What was my A open loop? So my A open loop was A naught upon 1 plus S by omega naught. Correct. So this was my A open loop. And now if I try to check the feedback factor, right? So beta. So now what will be the value of beta? So I am taking the feedback from output. What part of that output comes back to the input? This is what my feedback factor is. So now you can see this is nothing but a resistor divider, because the current that will be going into the input terminal of the op amp will be 0. So the beta feedback factor will be nothing but R2 upon R1 plus R2. Correct. So now if I just try to write the closed loop equation, just give me a second. So now it will look something like this. V out by V in of S will be nothing but the open loop gain A naught upon 1 plus S by omega naught divided by 1 plus beta is nothing but R2 by R1 plus R2 into, I have to multiply it, A naught upon 1 plus S omega 1 plus S by omega naught. Correct. So now if you try to simplify this equation, right? So now how will it look like? It will look something like this: A naught upon 1 plus A naught into R2 by R1 plus R2, correct, into 1 upon 1 plus S by omega naught into 1 plus A naught R2 divided by R1 plus R2. Correct. Though I have written this equation, it absolutely makes sense to do some kind of sanity check on this equation, right? So now what sanity check I will be doing? Let's try to put S equal to 0 just to check whether the DC gain that we will be getting from this equation is correct or not. If I put S equal to 0, this term just will become 1, right? So I will be just left with this particular term. Correct. And now what did I tell you? The open loop gain, the loop gain A into beta is usually much higher than 1, almost 10 to the power 4 or 10 to the power 5 in the magnitude, right? So now what is this? This is again A into beta, correct, for the DC, not at any frequency, right? So now what you can see, I can just ignore this one factor over here, and what I can write this as this will, then if I just ignore this one factor, the A naught and A naught will get cancelled from here, and what I will be left with is just 1 plus R1 by R2. Correct. So now can anyone please tell me whether this is the gain that I should have ideally got if my A naught value is much higher? So is the expression for the DC gain is correct for this particular configuration of op amp or not? Is this correct gain? Is this the ideal gain that I should have got from this particular configuration of op amp? Guys, you need to respond. Come on, I don't want this session to be one way. We need to interact, right? Just a minute. Guys, are you able to see my screen now?
Yes.
Yes. Okay, can you please at least tell me till what particular slide were you able to hear me? Were you able to see this problem which was being solved by me or no?
Yeah, we
Yeah.
can see the problem which been solved by you.
Okay, what was the last thing that you were able to see? Just a minute. Yeah. Were you able to see these equations or no?
No.
Yeah, but not clearly.
Okay, so I will just explain this slide again. So now what we have done is, the closed loop gain, right? So the closed loop gain is basically nothing but the open loop gain divided by 1 plus loop gain, right? 1 plus loop gain is nothing but a into beta, correct? Now our open loop gain is nothing but the DC gain upon this particular factor which rolls off the gain of the op amp in the open loop, right? And the beta is nothing but the feedback factor that we have, R2 by R1 plus R2. So now what I did is I just inserted these two equations of beta and the AOL in this particular equation because we are interested in the closed loop response, right? And when you put these equations over here, right, you will be left with this one particular big equation. Now if you try to simplify what I have done over here, the entire DC gain has been taken out over here, correct, and the 1 plus 1 upon s whatever is there, so that term is left on this particular side. So now what I was just trying to tell is that when you do some sanity check, we just want to check whether this equation is correct or not, right? So first of all we try to do some simplification. What did we say is the a into beta is usually much greater than 1, at least at the DC, at 0 frequency, right? So now I can ignore this factor of 1 over here. So the a naught from this and a naught from these are gonna get cancelled, and what you will be left with is 1 plus r1 by r2. So when you put s equal to 0 in this equation, this term that you are seeing on the right hand side, it will just become 1, and what I am left with is 1 plus r1 by r2. Can anybody please tell me whether this is the ideal gain equation for the non-inverting op amp amplifier or not?
Yes.
Yes.
Yes, correct. So that means whatever equation we have derived, it actually intuitively makes sense, right? So now at least this sanity check has been confirmed. So now what is our job? So first job is to basically we will try to simplify as much as we can. So this thing that you are seeing over here, now I will put this simplification in this equation. So now what I will be left with is V out of S upon V in of S will be nothing but 1 plus R1 by R2, right? 1 upon, again you can see the same factor 1 plus A naught R2 divided by R1 plus R2 is present over here also, and I'm also gonna ignore this 1 from here, right? So now what I will be left with is 1 plus just a minute, I will be left with 1 upon 1 plus S by omega naught into the A naught R2 upon R1 plus R2. Correct. So this is the equation with which I will be left. So now what you can see over here, what is the pole of this particular system, the closed loop equation? So the pole will be nothing but omega naught into A naught R2 upon R2 plus R1. Right, so this is what I will be left with. Let me just quickly check whether this is correct or not. So yeah, so it seems to be correct at least as of now. So now what we need to do is we need to give the unit step input for this to this particular equation. Now that unit step input is nothing but will be coming from here, right? So that unit step input will be coming from here. So now what I have to do is I have to write V out of S is equal to, if I am giving the unit step input, right, and if I take the Laplace transform, then I will be left with the factor 1 by S, correct? So additional 1 by S will be coming from V of S over here, right? So now 1 by S into 1 plus R1 by R2 into this factor over here, 1 upon 1 plus S by omega p. Correct. Now there are two ways to calculate the steady state value. Okay. So now what are the two ways So you must have studied in the Laplace transform that there is something called as the final value theorem, right? So what is the final value theorem? The V out at time t is equal to infinity is nothing but limit as s tends to 0 s into V out of s. Everybody remembers this equation from your signals and system course?
Yeah.
Great. So now let's try to do that. Now if I multiply s into V out of s, this s and this s is gonna get cancelled. So what I have to do is limit as s tends to 0, 1 plus r1 by r2, 1 upon, if I have to put s equal to 0 over here, right? So this is what I will be left with. So now what you can see over here, at time t is equal to infinity, I will be just left with this particular value. And one more thing, I have assumed the unit step amplitude to be u of t, but actually it may be a into u of t, some amplitude over here, right? So that a also I have to include over here, correct? So this is where that a will also be getting multiplied over here. So now the final value that I will be left with is nothing but a into 1 plus r1 by r2, correct? This is V out of t is equal to infinity. I hope till this point it is very much clear to everyone. Now what will be the general equation? So the general equation will look something like this. V out of t will be nothing but something like maybe a into 1 minus exponential of minus t by tau, correct? This is how the final expression will look, something like this, into of course u of t, correct? Because we are starting at t equal to 0 now. Yeah. So now this is the final expression that will actually look like this. So now we know the final value, right? So the final value, how to calculate the final value? If I put t is equal to infinity, this exponential is just gonna die down, right? And I will be left with just value a. That value a is nothing but this particular value, right? I hope it is very much clear. So now what they are asking us is a time, basically they are asking us to calculate, just a minute, let me just go back over here and let me just see. So they want us to calculate the unity gain bandwidth, and as well as they want us the settling time to be less than 5 nanosecond, correct? So now before that they are asking us to calculate the time required for the output voltage to reach within 1% of the final value. We have seen what is that final value. A is equal to nothing but a, this is the amplitude of the unit step, into 1 plus r1 by r2, correct? So now this so now what we have to find out is we have to take the 99% of this value, that is 99 by 100, right? And now we have to then find the time from that exponential equation that we have seen. So I'll just tell you what we have to do. 99 by 100 times that value that we have solved, right? A into 1 plus r1 by r2. Now this will be nothing but a into 1 plus r1 by r2 into 1 minus exponential of minus t by tau. Why I have put this over here? Because this is the final value that we have got, right? And they want us to calculate that time where the value will reach 99 by 100 times the final value, right? So I hope this is clear why I have inserted the equation like that. So now this is gonna get cancelled from over here. So what you will be left with is e to the power minus t by tau is nothing but 1 by 100. Correct. So if you take the log on both the sides and if you calculate that t 1% settle 1% time, right? So you will be left with tau into ln of 100. Now our next job is to calculate what is this value tau. Correct. What is this value tau actually? So now we have seen what is the value of pole, right? So our pole value is nothing but this particular value, right? This value that we have calculated already. So now our tau is nothing but 1 upon this omega p. Correct? Our tau is nothing but omega p. I will just give you an intuition for this. As my 3 dB bandwidth increases, right? As the 3 dB bandwidth is gonna increase for my amplifier's response time is going to be lower. So if I give a square wave of 10 megahertz, the example that we have seen, right? If I give a 10 megahertz square wave and my amplifier was reacting fast enough, now if I increase my 3 dB bandwidth of the amplifier, the same amplifier can also react very fast to 20 megahertz square wave as well. Correct? That is why this tau that you are seeing over here, it is 1 upon omega p. And how will you get that? So you have to literally do the inverse Laplace transform and you literally have to convince yourself that tau will be coming as 1 upon omega p. I will just leave this as a homework for you. If you don't get it, then come back to the next lecture and I will try to solve it in front of you. Right? So now what we are left with is, of course, this equation is here, and we want this t1% to be 5 nanoseconds. Right? Now I have 5 nanoseconds is equal to ln of 100 into tau is nothing but 1 upon omega p. Correct? Now let's try to put the value over here. So now what I will be doing is 5 nanosecond upon ln of 100 will be equal to 1 upon omega p will be nothing but 1 plus r1 by r2 into 1 upon a naught omega naught. Correct? So this is the equation that I am left with. Now they have given this value to me. Remember in the question, they have given this value to be around 10. So I know this value. And what they are asking is to calculate the unity gain bandwidth product. Right? So we have already seen that the unity gain bandwidth, just a minute. Yeah, we have already seen this. The unity gain bandwidth ACL into omega CL is always equal to AOL into omega OL, given that this is only a one pole system. And in the question, they have given it as a one pole system. Right? So now this value is already 10. A naught into omega naught is my open loop gain into open loop 3 dB bandwidth. And this is the gain bandwidth product that I actually want to find out. Right? So now what I am left with is 1 upon a naught omega naught. This is the term that I want to find, will be equal to 5 nanosecond divided by ln of 100 into this 1 plus r1 by r2 is 10. Correct? So now if you try to solve this equation, this value a naught omega naught will be coming around to be 9.21 gigaradian per second, or if you try to calculate it in the absolute frequency terms in the hertz, it will come out to be 1.47 gigahertz. So what did we achieve by solving this question? So first of all, this question is one of the basic examples that actually dictated the spec on the unity gain bandwidth of the op-amp. Right? So we wanted to design one non-inverting amplifier, and for designing that non-inverting amplifier, there was a requirement for having a particular settling time. Right? And from that settling time requirement, we were able to derive the spec on the two-stage op-amp that we want to design, that we want to put in the feedback, so that that non-inverting amplifier can settle within the particular time that the question has actually asked us. Right? I hope till this point it is very much clear. Any doubts for this particular question? If no, then I will just go ahead, because we have a lot of numericals to cover today. If at any point of time, if you guys have any doubt, then please feel free to poke me. I may not be able to look at the chat section. Just a minute. Hey, can you please mute yourself? Yeah, thank you. Yeah, so now what we'll be doing is the
No, but hey, we were discussing about the PVT variations
correct.
actually before your laptop got hanged.
Correct. So what do you want to ask about that, the PVT variation?
No, but just I was asking if we were discussing on that, and then after this started, we were continuing to the.
Oh no, we are not cutting actually. So what I had discussed over here is that this gain of this amplifier that you are seeing, the GM into RD, it can easily vary by 10 to 15%. Somebody is causing a lot of disturbance. So just give me a minute. Okay, hopefully that person doesn't unmute himself or herself. So yeah, what we saw is there is almost 10 to 15% variation if you try to fabricate this, right? And this is what we have told us. If you fabricate 10,000 such amplifiers on 1,000 different silicon samples, you will get a particular variation around your mean value, right? Now what did I tell is, if you put this amplifier in a feedback, right, and ensure that the product of A into beta is much greater than 1, then the gain of the closed loop system just depends on the feedback factor. So the variations that you were able to see in the open loop amplifier, those variations will be highly suppressed the moment you put that high gain amplifier in the closed loop manner. This is what actually I was discussing. Is it clear?
Okay. Yes, yes, it is clear.
Okay, great. So now we will move on to the next problem now. Just a minute. Yeah. And by the way, thanks to the person who actually messaged me on the Teams, because from him only I came to know that actually I got dropped from the meeting, because after that my laptop started to hang. Before that I didn't know what actually happened to the meeting and to the laptop. So now what, this is a question. So why I'm bringing this question, because you will see there is one more case study about the importance of the loop gain analysis, and in that loop gain analysis and some filter questions, right, I will be needing this concept. So now how to assign the signs, that is the positive and the negative terminals of the op-amp, to make the complete feedback as a negative, right? So even though the BJT has been given over here, so I want you to assume this to be MOSFET, or if you are comfortable with the BJT, just be comfortable with it. So the prerequisite for solving this question is basically, if I give an input at the gate of the MOSFET and take the input from the drain, you have to know that there is a 180-degree phase shift between the input and the output. Correct? Now on the other side, if I give the input to the source of the MOSFET, and if I take the output from the drain, there is absolutely no phase shift. Correct? And other case is, you give the input over here but take the output from the source here. Again in this case there is a 0-degree phase shift between the V out and the V in. So I want all of you to know this. If you don't know this, then I highly recommend just please revisit your analog circuits notes and just have this concept in your mind, right? So now what is the procedure to solve this question? So now the way we solve this question is, we apply some disturbance at any particular node, right? And then basically we come back to the same node again. And if we want this feedback to be negative, what is the job of the negative feedback? Negative feedback, if any change that I apply, any disturbance that I will try to provide on the negative feedback system, the system will try to reduce that disturbance, right? This is the principle of the negative feedback. So now if I am increasing the voltage over here by injecting some noise or by injecting some signal, the negative feedback loop should try to suppress it. So when I come back, when I traverse the loop and come back to the same point again, it should reduce. The negative feedback system should try to reduce the voltage on this node, so that this increase and this decrease actually gets cancelled out, right? So I hope that particular point is clear. So now if I increase the node voltage at this particular point, since I am giving the input at the gate, I am taking the input as a source, or for the BJT I am giving the input at the base and taking the output at the emitter, there is absolutely no phase shift, right? So if I increase this voltage, even this voltage is going to increase, right? If this particular part increases over here, what I actually want, I want this part node to go down. And if I want this node to go down, what should be the sign of this particular terminal, negative or positive? What do you think?
Should be negative.
Should be
Negative.
Negative.
Great, very good. So now if I increase the voltage on the negative side, then only the output can reduce and this disturbance will be completely gone, right? So this question is clear. Now let's try to come back to this particular question, right? So now what we are doing over here is, it is like we are giving the input, just a minute, we are giving the disturbance, let's say at this particular point, right? Now we are taking the output from the drain or from the collector of the BJT, right? And you know that there is a 180-degree phase shift. So if I increase the voltage at this point has to go down, right? And if this point goes down, and what I want, even this particular value over here has to go down, right? Because I want to cancel out the disturbance. So now if this voltage is going down, even I want this voltage to go down, so there has to be a positive sign, right? Because if I put a negative sign over here, then this value is gonna go up and the system will turn out to be positive feedback, right? So I hope that particular point is clear. So this has to be plus and this has to be minus in this particular case. Where will you appreciate this, where will you see the applications of this concept? So in the topic called as the low dropout regulator, as well as the filter topic. If you look at the higher order filters, right? So we will see some examples from those topics. So in these topics, you will see that there can be 2 or 3 op-amps that are in the cascade. So now how can I determine the sign of each op-amp so that the feedback is still net negative, right? So I hope that point is clear. By the way, this I will leave as a homework for you, because we have already seen the methodology and these examples again are very easy, right? So I hope that part is clear. Now let's see a classical application of whatever sir has told you about the loop gain analysis, and let's try to bring it into the domain of the power management integrated circuits, that is the low dropout regulator. So now where do you see the application of the low dropout regulator? So what I have shown on the left hand side is the circuit diagram of something called as the phase locked loop. What is the job of the phase locked loop? If you remember from your last class, right, we have seen if you are trying to transmit a LTE signal from your mobile, somebody has to generate the 900 megahertz carrier signal. That carrier signal is generated by the loop called as the phase locked loop, right? And this is the internal structure of the phase locked loop, correct? I don't want you to get confused. Don't, even if you don't understand anything, that is still okay. But what I just want to tell you is that there are so many different blocks that are present. Again, it's a negative feedback system. There is a divider. Somebody is giving some signal into this divider. There is a voltage controlled oscillator. There is a phase frequency detector as well as the charge pump. Now, each of them needs its own supply, because this part that you are seeing over here, it has a high digital activity. That means what? It will have some switching activity at particular frequency rate. If I don't isolate my supply, right? If I don't isolate my supply, then this switching activity that you are seeing over here, this particular signal can get coupled through the substrate and can be present on the supply voltage of your VCO or the charge pump, right? Now what can I do? I can have a regulator with me which can take some kind of ripples on the supply voltage, and it will give me a very clean output, right? So that is the job of the regulator. And now, so I have to have a regulator which can give 2 or 3 different VDDs for this voltage controlled oscillator, this divider, this charge pump, as well as the phase frequency detector. Again on the again on the different side, if you look at the application in the ADC, that is analog to digital converter, you have a comparator over here. You have some logic, the digital SAR logic that is actually going on, which gives the its output to the DAC. Correct. Now again, I want to have these supplies to be isolated. Correct. I don't want ripples that are being caused by the digital activity to disturb any of my supply, or else the entire the output that you are seeing over here, it will have those switching components present, and I don't want that to happen. Correct. So now what we need to do, we need to have one LDO that will give me a very clean supply. Right. Now if you look at the internal architecture of the LDO, first of all, whatever we have done the last time, right, let's try to check whether this feedback that you are seeing over here, whether this is negative or not. So if you go into the circuit details of this, so let's first try to check whether this is a negative feedback system or not. Now what I will be doing is, I will be increasing the disturbance over here. Correct. I am giving the input at the gate. I am taking the output from the drain. There is a 180-degree phase shift, so this node has to go down. Right? If this node goes down, even the node X is gonna go down. If this node goes down, correct, then what is going to happen? Again, this node tries to go down. I try to increase the disturbance over here. The feedback system actually decrease the disturbance. So we can see that there is a negative feedback that is present. Correct. So now how does this feedback actually functions? So basically you try to check the V out, right, where you want to give a clean supply, right? You sense that voltage, apply it to your op-amp, and there is already a very good reference voltage that is actually present. And who generates this reference voltage? So this V reference that you are seeing, it is actually generated by a circuit called as band gap reference. This reference voltage has to be so accurate that despite the PVT variations, you should not be able to see any change in this V reference. Correct. So now again, just try to connect what we have seen in the first class and what we are doing right now. All the dots are coming into the picture, right? So now how does this function? So it tries to sense the V out voltage, and basically it tries to what you can see, it tries to give the input to this MOSFET in such a way that if this V out actually increases, if some disturbance comes up, then this MOSFET will ensure that a current has been injected which will try to decrease this V out voltage. I won't go into a very much detail because that it will take a complete 1 hour class to explain what this circuit is actually doing. Now we will try to do some loop gain analysis on this circuit, and we will see how much this circuit is capable of rejecting the ripples that are present on the input voltage by giving us the clean supply on the V out. Correct. I hope the target is absolutely clear. We are trying to do some loop gain analysis over here. So now how can I proceed over here, right? So I want to do the loop gain analysis. So how to do the loop gain analysis? You need to break a loop at a high impedance node, right? So that you don't have to take the loading effect into the accounts. So now we will break a loop over here, correct? We can break the loop definitely over here and apply some voltage called as the V test, right? Now if I give a V test over here, what will be the V out that I will be getting, correct? So now if I just try to redraw circuit a little bit, so now what I am doing is, this is the PMOS transistor that I have. I am applying some V test input over here, correct? And when I am applying some input, some disturbance, other sources has to be shorted, right? So now this is a small signal ground that I have, and then what I have at the drain of the MOSFET is this R1 and R2, this R1 and R2, correct? And at the same time I have the load over here, correct, which I can represent by RL. I have a load over here which I can represent by RL. So now what you can see over here, I am giving the input at the gate, I am taking the output from the drain. This is nothing but a common source amplifier with a load resistor. What is the equivalent load resistance? If I look at this particular point, it will be nothing but RL parallel R1 plus R2. I hope everybody agrees with that. And now if I try to get the gain of this circuit, it will be nothing but minus GM into this particular factor. So this factor will be nothing but what? V out by V test. So I gave the input at the gate, I got the output over here. But again I have to do a loop gain analysis, right? Again I have to come back to the same point. So now if I try to go from here to here, first this whatever voltage is there, it is actually getting divided between R1 and R2. So now if I try to calculate the value Vx, right? So the value Vx will be nothing but V out into R2 divided by R1 plus R2.
Hey,
Right?
excuse me, can you please use a larger, bigger pointer? It's like unless until you write, we are not able to see where you are cursing over. Like where is
I
your
don't
cursor?
know how to increase this pen that you are seeing over here. We don't
Yeah,
have
yeah.
any option over here to increase the size of that pen. I mean, wherever I am writing, right?
Okay.
So I literally
Uh-huh.
don't have any option for that.
Sure.
Yeah.
Okay.
So now let's try to get back. So now what is the V out? V out is nothing but minus GM into RL parallel R1 plus R2, correct, into V test. This is V out, right, into V test. And now I have this R2 by R1 plus R2 factor as well. R2 divided by R1 plus R2. So now this is the value of Vx. This is the value of Vx. But from Vx I have to go here. Again I have to come back to the same point, right? So now what I will be doing is, from here to here, from this positive terminal of the op amp to the output, we just have a multiplication by the factor of A1, right? And then we will reach back to the same point again. Correct? So now the VO is nothing but the output of the op amp, is nothing but I just have to multiply the Vx by the factor of A1. That's it. Nothing more than that. So now if you do it, what you will get is minus GMA1 into R2 by R1 plus R2 into R1 plus R2 parallel RL into V test. Guys, at any point if you have any doubts, please feel free to poke me. I may not be able to read the chat section. So now this is the output that we got, and how we define the loop gain. We first give the test voltage at the point, and then we again came back to the same point. So whatever signal we got, if we divide both of them, that is my loop gain, right? So now if I divide VO by V test, so my loop gain will be nothing but minus GM into R2 upon R1 plus R2 into A1 into R1 plus R2 parallel RL. This is assuming that my op amp is ideal. We will also check what happens when the op amp is not ideal. Okay, that is the part, but let's do step by step. Correct. So now once this loop gain is clear, now this is a negative feedback system, right? How to calculate the closed loop gain? So A closed loop is nothing but A open loop divided by 1 plus loop gain, right? And this is the reason why we calculated the loop gain first, because we want to check the closed loop gain, and to get that we first have to know the value of loop gain. Now how to calculate the open loop gain? So the open loop gain, you can see open loop gain, the way to calculate the open loop gain is basically just remove the whatever feedback is coming up, right? So this point that you are seeing, this is where the feedback network is injecting its signal. So if I just null or short this node, right, then nothing will be coming up from over here, right, and then I will be able to calculate the open loop gain. So what I will be doing is, since we are shorting them, since you are shorting over here, nothing is going to come up from this particular side, nothing is going to come up from this particular side. So this A1 is redundant now, because whatever output we are giving, right, it will be coming to A1, it will be getting amplified, but nothing is present, nothing is gonna happening to this node, because we have forcefully shorted it because we are gonna check the open loop gain now, correct? So now if I, so basically this part actually became redundant, and the circuit to calculate the open loop gain will be reduced to something like this. This is my PMOS that I have, correct? This is the Vin. Remember, the input is connected to the source of the MOSFET, right? This is where the ripples are going to be. So now again we have R1, we have R2, and again I have RL in parallel, correct? And this will be grounded now. Correct? Why grounded? Because we have shorted it, right? Because we don't want any feedback to come up over here, because we are, this is the open loop gain calculation. So now a open loop gain, if you look what it will be, we are giving the input at the source of the MOSFET, we are taking the output from the drain, there will not be any phase shift now, right? So, and what will be the gain? The GM into the effective load resistance. What it will be? RL parallel R1 plus R2, correct? I have the loop gain with me, right? I have the open loop gain of the system as well. Can I substitute A and B in the equation number C to find out the closed loop gain or not, right? We can definitely do that, and this is the exact step that we are going to do. So now if I try to calculate the closed loop gain of the system, that is V out by V in. So now the open loop gain is, we have calculated GM into RL parallel R1 plus R2, correct, upon 1 plus loop gain. Loop gain we have already seen, right? GM A1 R2 upon R1 plus R2 into RL parallel R1 plus R2, correct? And what did we say? The loop gain, just a minute, yeah, the loop gain is usually much greater than 1. If you look at the DC, it should be around 10 to the power 4 to 10 to the power 5, correct? So again we are gonna ignore the factor of 1 over here for simplifying the expression. So now what you will be seeing is, if I ignore the factor of 1 over here, this factor and this factor are gonna get cancelled out, right? Even this GM and GM is gonna get cancelled out. What I will be left with is R1 plus R2 divided by R2 into 1 by A1, or I can also write it as 1 plus R1 by R2 into 1 upon A1. This is my closed loop gain of the system. Now a very weird thing, right? So now if you take a amplifier, right, if you take a common source amplifier, and if you are using it for an amplification purpose, you want that gain to be as high as possible, right? V out upon V in is equal to GM times RD. It should be as high as possible if I am trying to design an amplifier, right? Now this is a closed loop system. The closed loop gain, this is basically V out by V in. Now I will just ask you a very simple question. If the supply ripples are present, right, if some disturbance is present on the V in node, do I want that disturbance to go to the V out node, or I don't want it?
We don't want it.
We don't want. So what do you think? This closed loop system should attenuate the thing, or it should amplify this particular thing?
Attenuate.
Attenuate, right? Very good. So now if you look at this particular expression over here, this A1 is the ideal gain of my op amp, right? What it will be? It will be something like 10 to the power 4 or 10 to the power 5. Correct? Now what you can see over here, because I have included that op amp and because I have a negative feedback system, the gain, the V out upon V in will be extremely low. Even if I assume that, let's say R1 will be few kilo ohms, right? Maybe 5 kilo ohm, and maybe R2 maybe something like 10 kilo ohm, correct? So even if I assume it something like this, so now what this equation will be reduced to 1 plus 5 by 10 is 1 by 2 into 1 upon A1 is let's assume 10 to the power 4. So this is 10 to the power 4, right? So now what you can see over here is the V out by V in is very close to 0. right? And this is the job of the feedback system, to make sure that none of the ripples that are present on the wheel are gonna come back to the node V out, right? Now, one more thing, if you look at the open loop gain, right? If you just look at the open loop gain that we have, if we don't have any feedback in the system, then whatever is going to be there on the wheel, what this MOSFET will do, it will just amplify the ripples with this particular gain, the open loop gain, and it will produce these ripples at the output, the amplified version of these ripples, right? So now if we didn't have the negative feedback system, the ripples would have been amplified, but because we have the op amp and the negative system around it, the ripples are absolutely reduced by the factor that 10 to the power 4 or 10 to the power 5. I hope you appreciate the importance of the negative feedback now. Now this is just for the DC that we have seen, right? Now what we have to check is what happens at the higher frequencies, correct? Now for the op amp, I can assume this model, right? A1 is equal to A naught upon 1 plus S by omega naught. The same thing that we have seen in the first question, right? Now what if I put this equation in the closed loop expression that I got from here? The A1 is in the denominator, right? So what if I put that A1 with this particular equation, right? So now what you will be left with, if you put this V out by V, this is the closed loop gain, is 1 plus R1 by R2 into 1 by A naught into 1 plus S by omega naught. Correct? Can anyone please tell me what will happen to this transfer function? What is going to happen as frequency increases? Will this increase or will this decrease?
Increase.
Increase, right? And can you tell me why, if this function increases, then what does this mean? V out is equal to V in into, let's say, some factor X. If X increases with the frequency, then what do you think, what is going to happen with the ripples over here? Are they gonna get amplified and then they will be reflected by the V out, or they will be getting attenuated?
They will be amplified because if it is increasing.
Correct, very good. So as frequency increases, right, so the ripples that I will be expecting at the output, they are gonna increase. And why did this happen? Again, let's come back to the loop gain that we had calculated, right? So this is the loop gain that we have calculated. This was the A1 over here. Now if I replace this A1 with A naught divided by 1 plus S by omega naught. Now can you guys please tell me what will happen with the loop gain as the frequency increases? Will it decrease or it is gonna
Reduces.
It reduces, right? That is absolutely good. So because my loop gain has reduced now, so my loop cannot react very fast, right? And because of that, and because my loop gain has reduced, and you know the closed loop gain, right? The closed loop gain is nothing but A open loop upon 1 plus loop gain, correct? So now because the loop gain has started to decrease, the ability of the feedback system to get these ripples and to reject them is also decreasing with the frequency. And this is what this equation is actually highlighting. As the frequency of the ripples is going to increase, the loop won't be capable of completely rejecting them, so you will be able to see some small ripples that will be present at the output. So this is what this LDO actually works. You can, and if you ask me, will this keep on increasing infinitely, then answer is no, because though I have not shown in the diagram, right, there is some output capacitance CL that is present over here, and that will ultimately make this line that you are seeing over here, it will make it flatter, and after some point it will even fall down. The reason for this, you have to go into the power management course, right? What I just wanted you to highlight is to appreciate the importance of the loop gain, how it helped us to calculate the power supply rejection ratio of the LDO, and what happens if the loop gain decreases when you try to increase the frequency. Even the ability of the LDO actually drop to reject the ripples, right? I hope till this point it is very much clear. Any doubts, guys? We are going to take a break of 4 or 5 minutes after this. Any doubts at this particular point? Any doubts? Anything yet that you didn't understand from whatever I taught?
Yes, sir. Understand, sir. Sir, the same ripples will appear in voltage regulator. No, sir. Linear regulator.
No, not exactly same ripples. If you look at this factor, right? What is this factor? This is like 1.5 into 10 to the power minus 4. So this is the amount of attenuation that your loop was actually providing to the ripples when the frequency was very low. Now this factor that you are seeing over here, this factor will actually start to reduce as you increase the frequency. So it is not as if the ripples will be coming as it is. Of course some attenuation will be there to those ripples, but that attenuation will keep on decreasing as you increase the frequency of the ripples.
Okay.
Yeah.
Hello, sir. Could you please tell me means how to find this open loop gain? Means we have broken the loop at the gate of the PMOS, but how to decide where to break the loop?
Okay, so you
Means
can literally
we have
break the loop anywhere. The only thing is that node should be high impedance node. Or if you don't break it like that, then the problem is some loading effects come into the picture, which I don't really want to go over there, because that part is there in the feedback concept. I don't know whether this course will cover the feedback or not, but if you open the chapter of feedback in the Razavis, the design of analog CMOS integrated circuits, right, you will see that we usually don't break the loop at low impedance nodes. So that is why I decided to break here. You can also break the loop here, but the only thing that you should understand is whatever signal from the feedback is actually being fed, right? Whatever the signal, let me just have the diagram again, just a minute. Let me draw it somewhere. Yeah, so this is your A, this is your feedback factor beta, right? This just have a look at this summation, right? This is the Vin where I was applying Vin, and this is the negative feedback that I was applying. So now to calculate the open loop gain, what I did is I just nullified this feedback directly. I don't want this feedback to come up, and that is the way that I've tried to find out the open loop gain basically.
so if we break the loop at node X, that is the input of the op amp. So in that case, R2 will get R2 will not become into picture, no?
Just
could
a
you-
minute. Yeah, so
Yes.
you're saying break the loop here.
So yeah, so means X node will be grounded or the further next
See,
node.
you can literally break the loop anywhere, but the
Yeah.
point where the signal from the feedback is coming to that plus sign that I showed you in the closed loop system, right?
Yeah.
Right? This is the input, and this is from where the feedback is coming up, right? So
Yeah.
that point,
Yeah.
where is this point actually? This point is occurring here, no?
Yeah. Okay. So you are saying that if I break the loop at the non-inverting of the op amp, then non-inverting terminal of op amp will be grounded and X will be floating.
Just give me a second to think about it. What did you say? You want to open the loop here, okay?
Yeah. And then if we open the loop here, then the non-term means positive terminal of the op amp will be grounded and X will be floating.
The X over here. Okay, this is what you're talking about. Okay, so first of all, you have to reduce the Vref over here, and if you just ground this, right?
Yeah.
If you just ground this, then what will be coming up over here then?
So actually, what I am saying, like what you have done,
Just
you
a
have
minute.
shorted the gate of.
Just a minute. Yeah, go ahead now.
You have shorted the when you have opened the loop, then you have shorted the gate of the PMOS.
Yeah, the
if-
reason why I
yes.
shorted this because I
Yeah.
don't want
Yeah.
any feedback to come over here. That's it.
Okay, so that point I got. So means my doubt was that if we open the loop at this positive terminal of op amp, then the positive terminal of op amp will get sorted, or X terminal of the R1 and R2
X
will get
terminal,
sorted.
the output terminal of the op amp that you are seeing over here, this is where I shorted it completely.
Okay, so you are saying that gate and output of op amp both will get shorted.
The gate as well output of, yeah, obviously both of them are gonna get shorted because there is nothing present over there, right? No network
Okay,
is present over there.
so if we follow this this approach, then this X terminal will get shorted. Then our open loop gain will not get changed because R2 will not be coming in picture.
Okay, I got where you are coming. Okay, so that's a good question. So now this network, so basically the doubt entirely is what should be considered as the open loop and what should be considered as the feedback, right? This is your doubt.
Yeah.
If I try to represent it in the one statement, correct?
Yeah.
So now you can just break the loop. You can take this complete part as a feedback. You can also take this particular only a very small portion as a feedback, or you can do any combinations. The only thing is the final answer is not going to change. So what I will do is I will take this example, not right now because of the short of time, and during the next class, or maybe when I upload the notes, right, I will tell you how considering the let's say if I take that R1 and upon R2, and if I don't consider it in one case, so how changing the how changing the amplifier and changing the feedback, what to take in the feedback and what to take in the open loop, even if I change it, the final answer is going to be coming exactly same. I will show you,
Okay.
just give me some time by tomorrow.
Okay.
When I
Okay.
upload the
Sure.
notes, I will definitely put that example in at the
Okay.
end
Sure.
actually.
Sure. Thank you.
Yeah. Okay, guys, just give me 2 minutes. I will just get freshen up and come back again in 2-3 minutes. Yeah, so now what we'll be doing is now we will try to solve some problems on the RC filter, because as you have seen in the second assignment, some question on the filter has been asked, right? So now we will try to first get some feel for the passive filter, then we'll go into the active RC filters, and then we will dive into some of the case studies that are there in the very recent research papers, and just try to see whether at least we are able to identify the active RC filter structures or not, right? So now the way we will be solving the questions is, right, so first of all, if it is just a passive first order RC circuit, right, if it is a passive first order RC circuit, then you can just inspect the location of the poles and the zeros just by looking at the circuit, right? And how to do that? So now if you look, let's say this is the way I have arranged the circuit, right? If I try to do the ratio V out by V in, what it will be nothing but the impedance divider, right? ZB upon ZS plus ZP. Now I can do one thing. So now what is the meaning of the pole? What is the meaning of the pole? The output actually goes to infinity, correct? They're in the response, right? So now what does this mean? If I just put ZS equal to minus ZP over here, correct? If I just put ZS equal to minus ZP, why? Because the denominator will be becoming 0, and then only I will be getting what we define as a pole. This is the basically the definition of the pole, right? So now when you put ZS equal to minus ZP, right, you will get the pole just by doing this. So if there is some complicated network that is present like this, you just have to do this particular thing to get the value of the pole. Now what about the 0? What is the definition of the 0? The output has to be 0 at that particular 0 frequency, right? So now what can I do? I can put ZP equal to 0, right? But just remember, if I put ZP equal to 0, at the same time ZS should not be equal to 0. Can anyone please tell me why this is the case? Why did I put this condition?
If both are 0 means numerator and denominator becomes 0, then it is undefined value.
Undefined,
Sir.
or it can become finite also, right? You must
Sir,
have studied
such a-
in your calculus cell hospital rule, right?
Yes, sir. But in reality, if pole is not exist, then there is not possibility for circuit. No.
Sorry, I didn't get that.
If pole is not present, if ZS is equal to minus ZP, pole will be 0, no, sir. So in that case,
Oh.
in reality, such a system will not exist, no, sir. If pole is
Such a
not there.
system will not exist. No, pole will be always there. No, so if you have R,
No. I think he might be saying this, that if there is no pole, then we cannot expect 0 at all.
yes, that is
0 is
absolutely
there.
true. That is absolutely true. That is absolutely true. You are absolutely correct, because the output will be unbounded in that particular case. It will just keep on going, and that cannot happen with the LTS systems. You are correct. Yeah.
Yes, sir, that was only.
Yeah, great. Thanks for the clarification. Yeah. So now we put this condition. Now another condition you can put is ZS equal to infinity, so that this term becomes 0. But at the same time, my what you can say, this thing should not be infinity. Correct? It should not be infinity, or else again I will be having infinity upon infinity form. Correct? I don't want that to happen. So just remember these three conditions for finding the pole. This is the condition. for finding the zeros, we will try to enforce these two conditions, right? And I will also tell you some tricks as we solve the questions, right? So just remember these three conditions as of now. So now what we'll do, we'll just solve few examples from the Razavi's book and just try to see what is this, correct? So now this is my Z1, this is my Z2. If I just have equate the negative of this to each other, R1 will be coming out to be equal to minus 1 upon SC1, correct? So my pole frequency will be nothing but minus 1 upon R1 C1. Correct? Now, does there exist any zero in this particular circuits? Let's try to check it. When can the output become zero? So first of all, I will try to enforce this to be equal to zero. When can 1 upon SC1 become equal to zero? At infinite frequency. A zero at infinite frequency is not a danger to me because we don't even take it into account, right? At the same time, if you look for this particular thing, right? Can this become infinity? Absolutely no, because we have a finite value of R1. Right? So this is the pole that we got, and we, even by just looking at this equation, right, you can just guess that what will be the response that I will be getting. So 1 upon SC1 divided by R1 plus 1 upon SC1. So now if you just multiply, you will be just getting 1 upon 1 plus SCR1. Correct? So this is the transfer function for the first circuit that we got. Correct? And this is exactly confirming the same thing, that it just contains one pole. Right? Now if you move on to this particular case, right, again this complicated network is my Z1, again this is my Z2. If I equate negative of each other, negative impedance of each other, so what I will be left with is 1 upon SC1, that is negative, will be nothing but R1 parallel 1 upon SC2. Correct? And now if you solve this, so you will get the pole to be minus 1 upon R1 into C1 plus C2. Now there is one more way, one more shortcut to find the poles. And by the way, this I have learned from, I don't know how many of you know, but there is ex-BITS professor called as Chambian T. You can follow him on LinkedIn as well. So this method I learned from him, right? So now what you can do is, see what is the pole. The meaning of the pole is nothing but at that point the response should go towards the infinity, correct? That means the V out of S upon V in of S, right? So now it should be reaching towards the infinity. Now at the same time, how can this happen? I can do one thing, the whatever V in node is there, right? I can just short it directly and then calculate whatever is present at the output node. So if I take that circuit, just a minute. Yeah, if I take this circuit, right, and short the input to the ground, this is what I will be left with, and this is what I have C1 over here. So now whatever is present on the V out, right, so now that is going to become your pole. So now what you can see is that this node, what you can see is C1 and C2 are in parallel with each other, right? And you have R1 that is parallel to the parallel combination of C1 and C2, because this node is grounded now over here, correct? So what you will be left with is nothing but 1 upon R1 times C1 plus C2. So instead of solving from here, you can directly get the answer from this method, correct? So this you can do only for the poles, huh? This you can do only for the poles. So this is one of the shortcut methods that you can apply to find the poles very quickly, correct? Now let's go for this particular circuit. I will just draw it again over here. You have C1, you have L1, and you have R1 that is present. You have V in and you have V out. Now what I will doing, I will be taking this complicated network as a Z2 and this as a Z1, correct? So now we just have to equate the impedance like negative of each other to find the pole, correct? By the way, just give me a second. Yeah, for the previous case we just found out the value of pole now. Let's check whether there is any zero present or not, correct? So now how can we find out the value of zero? So first of all, if this capacitor becomes short circuited to the ground, the output will be becoming zero, but that can only happen at infinite frequency, so that is not a danger to me. But what about this? What about this, correct? So now again we will enforce the conditions that we have seen. The ZP is equal to 0 condition will not hold true over here because I literally have to operate at the infinite frequency. Let's try to check whether ZS becomes infinity or not. Correct? So this is the ZS, and what is the ZS? It is nothing but the parallel combination of R1 and 1 upon SC2. Correct? So now when can this become infinity? So now if you have, let me just tell you here, if you have Z1 like and have minus Z1 that are in parallel with each other, what will be the net impedance? Z1 into minus Z1 upon Z1 plus minus Z1. Correct? So what you can see over here, if I have impedances which are negative of each other and they are in the parallel combination, then the net impedance just reduces to value of infinity. So basically it becomes open circuit. Correct? Now what we wanted to enforce, we wanted to check whether the Z1 from here can become infinity or not. And when can that happen? If 1 upon SC2, if 1 upon SC2 becomes minus of R1. When this condition is enforced, then this thing that you are seeing over here, the parallel combination of C2 and R1, it will just become open circuited. And since there is a disconnect between the V in and the V out, the V out will be just equal to 0 because V in is not been able to connect it to the V out through any path, right? So the value of the 0 will be nothing but minus 1 upon R1 C2. Correct? I hope that is clear. One more way to look at this is if there are two paths between the V in and V out, right? If there are two different paths between the V in and the V out, just a minute. Why is it not updating? Yeah. So if there are two paths between the V in and the V out, the signals can combine at this node in such a way that, let's say this path gives 0 degree phase shift and this path gives 180 degree phase shift, right? Even though finite signal is traveling through both the paths, the net combination at the output is going to be 0, right? So this is another way to think about this particular circuit, right? So we have looked at it in many different ways. So it has a 0, it has a pole, correct? And so I hope that particular point is very much clear. Now let's go on to this particular case, right? So now what we are doing is we have to do Z1 equal to minus Z2. So now what is Z2? Z2 will be nothing but R1 in parallel combination with SL1, and Z1 is nothing but 1 upon SC1. So minus 1 upon SC1 has to be equal to R1 parallel combination of SL1. Correct? So now if you do it, alright, you will be getting a quadratic equation. Why quadratic? Because you can see it has a LC network, right? So now the equation will be reduced to R1 L1 C1 SP square. SP is nothing but my pole frequency plus L1 into SP plus R1 equal to 0. So you will, depending on the values of R, L and C, you will be getting you may get real poles, you may get the complex poles, or you may get imaginary poles completely, right? So I hope that part is clear. Now we will solve the next question. This is this particular question. Now let me just draw it quickly over here. This is C1, this is R1, correct? Then I have R2 and then I have C2. This is my V out and this is my V in. Correct? Now again let's try to think about the zeros first, right? What did you see? There are two parallel paths that can reach from the V in and the V out at the same time. If I can make them, if I can have an impedance in such a manner that the phase shift between these two paths is exactly 180 degree, I will definitely get a 0. Correct? So now we intuitively feel that there definitely exists a 0, and how can you calculate it? So this path that you are seeing over here, its impedance should go to infinity, so that there is no connect between the V out and V in, and V out will be just reduced to a value of 0. And when can that happen? These two impedances, 1 upon SC1 and R1, has to be negative of each other, right? So this will give me a 0 frequency. So my SZ will be nothing but minus 1 upon R1 C1. Correct? Now we have calculated the 0. Now what about the pole, right? So now I can consider this as my Z2 and this big network as my Z1, right? So now to get the pole, what can I do? Again, I can equate Z2 equal to minus Z1. I can do that, but we have learnt a shortcut method, right? Just short the input, and whatever impedance you will get at the V out, from there on you will get on the pole. So now if you short it, what you will get is, you have RL, correct? Then you have a C2. Again the C1 that was going here, it will come in parallel because I have shorted the input and you have R1 that is present. Correct? So now what you will be getting is the pole will be nothing but minus 1 upon this R1 and RL are parallel with each other, and the C1 and C2 will be nothing but just an addition because they are in parallel. Correct? So you got the pole frequency from here. So the circuit has 1 0 as well as the 1 pole. Correct? So now let's move on to the next thing. We don't have to calculate anything over here. They just want us to identify the type of the filter. Somebody was saying something. Any doubts? Okay, so we will go ahead. So now we just want to identify the type of filter over here. Correct? So now how can we identify? So we will check the corner case, right? So we know that if you look at the LPF response, it looks something like this. At s equal to infinity, ideally the response should go to 0, right? If you look at the high pass filter, I can say the same thing about the high pass filter. At s equal to 0, correct, I should get 0 only. It should not give me any response at the output, right? Now if I look at the band pass filter, what you can see over here is that at s equal to 0 the response is 0, at s equal to infinity
Yes.
also the response is 0. Somebody was saying something?
So I think he has joined.
About the zero, I think he just made the numerator zero, like 1 upon SC equals to 0. But that went to infinite frequency, so we don't care.
Yeah.
I made
So
mistake
we don't care
somewhere.
about the infinite frequency, so no zero exists.
Okay.
Hello, I made mistake somewhere.
Okay,
like what?
let me be clear. You're asking how he told there is no zero for the first example, right?
Based on what he had taught us on the theory.
Yeah. Basically, to get the zero, we should make the voltage output as zero, right?
Yeah.
For the first example, which he thought, like there was a resistor in series, but like, the capacitor was connected to ground and the V out, right?
Yeah.
Let's say like, the impedance
Guys, are
of
you
the
talking to me
capacitor
or
is
you are
1 by
talking to
CS.
each other?
Okay.
Let's say we should make the V out 0. Then the
Guys.
choice we have is to make the impedance of the capacitance 0. Okay. What's
Mm-hmm.
the value of
Hello?
So we should not configure like considering it as a practical 0. That's it.
Mm-hmm.
What we
Okay.
can say.
Hello, are you able to hear me?
Yeah, sir.
Yeah.
Yeah, so were you able to hear the explanation or I was muted for the entire session?
No, sir, we are able to
We
hear.
are waited for almost 10 minutes.
I was muted for 10 minutes.
Yes.
Before that only we couldn't see your screen.
shit,
I don't know.
You are not even able to see the screen.
Yeah.
Yes.
No,
You're not there. You left at the
we were
start.
able to see the screen, but whatever you were writing, we were not able to see that.
How can that happen? Let me just.
Sir, my idea
last
is,
example
even
only.
though even I faced the same issue, sir. You better to connect with your mobile hotspot. At that time, internet connectivity issue won't occur, so you will be very stable position.
Oh, okay, just give me a second. Just a minute.